All right, y'all. So, for the most part, you don't really need to go through every single detail of a function to check that it's continuous. If you're ever asked, where is this function continuous? It's not like I'm asking you to go at every single point on the number line and establish, oh, my left limit equals my right limit equals the general limit, which equals the function value. When you're asked if something's continuous, for the most part, you're looking to determine where is this function discontinuous, and let me leave out those values. So for the most part, pretty much any function that we can write down algebraically is going to be continuous except at any holes that are in the graph, any asymptotes that are in the graph, vertical asymptotes especially, and then any breaks or jumps that we might see occur. So some examples of nice continuous functions that are continuous pretty much wherever you want. Polynomials. Polynomials don't have any asymptotes. They're defined everywhere. They don't have any holes in them or anything strange going on. Cosine and sine of x, if you remember those graphs, so those are the kind of waves. They don't have any asymptotes or holes in them. Now, tangent, secant, they have some problems, but we'll talk about those in a sec. Exponential functions, nice, normal, continuous graphs. You can plug whatever number into them and get something out on the other side. They don't have any asymptotes. They do increase very rapidly, but that's not the same thing as a vertical asymptote where you're like dividing by 0. Logarithmic functions are also continuous where they're defined. So remember, if your function doesn't even have like a domain at a certain value, so like it doesn't make sense to say, for instance, that logarithms are not continuous for negative values, because logarithms don't even have a domain including negative values. So when you say that a function is continuous, there's a little bit of language beneath that where you're saying this function is continuous everywhere where it's defined. Where a function isn't even defined, we don't really care about. Rational functions, those are another type of function that are mostly continuous, except that they're vertical asymptotes where we have 0 divisors. And then linear and constant functions, so those are functions that are lines, or in the case of a constant function, that's just a horizontal line. Those are nice and continuous. They don't have any issues. And then tangent, cotangent, secant, and cosecant, those are mostly continuous functions. Mostly because all of those have an infinite amount of asymptotes. And just to make this a little bit more interesting, if you think about it, tangent of x not only has one vertical asymptote, it has an infinite amount of them. So you might be thinking, well, okay, like I kind of get it with rational functions because maybe we have 2 or 3 points where we have a vertical asymptote. But tangent, secant, they have an infinite amount of asymptotes, so why are we even talking continuity when we have an infinite amount of something? So it's a good little segue here to talk about the difference between things that are countably infinite and things that are uncountably infinite. And this can lead you into some relatively interesting, if you're really into math, YouTube deep dives, but there are 2 different types of infinity. There's countably infinite, and an example of something that's countably infinite would be the counting numbers or the whole numbers. 1, 2, 3, 4, 5, 6, 7. Those are considered countably infinite because relatively, given enough time, we could count every single one of those values. Now, if you have something that's uncountably infinite, that is actually a different degree of infinity. So if you ever had one of those arguments about like, oh, well, I hate you like infinity plus 1 or something, and it's like, the ultimate burn for a 3-year-old. Infinity plus 1 is the same thing as infinity. It makes no difference. But uncountably infinite and infinite, they don't even compare in terms of size. Something that's uncountably infinite is like the real numbers. So the real numbers are uncountably infinite because even if we could develop a process to try to write them all down, we would never hit all of them. There's just so many of them that comparing like the real numbers to a set like the integers is kind of foolish. They are just like one is basically a point, and you're comparing a point to like an entire plane. This problem relates to something called the continuum hypothesis, which is one of the oldest open problems in mathematics. In mathematics, an open problem is a problem that hasn't been solved yet. The mathematician Georg Cantor actually worked a lot on the continuum hypothesis, kind of a sad case. He was a brilliant mathematician, and he's the one that established that, hey, there is a difference between the countably infinite and the uncountably infinite. And then he spent probably around 20, 25 years trying to establish if or if not there was an infinity between those two. That's what's called the continuum hypothesis. And then later in life, he got a lot of, modern day term would be beef, for his ideas. So he had mathematicians that were publishing papers that were trying to contradict him. He had a lot of personal attacks levied against him. And over, I think, the span of 1 year, he lost around 90% of his family to a tuberculosis outbreak. So eventually he kind of just lost his mind and was committed. But his problem, the continuum hypothesis, is still an open one. So if you're interested in weird problems like that, that's kind of how I got started with mathematics. Definitely a good one to research. And if you are, exceptionally bright and talented and that appeals to you to solve it, the payoff is pretty enormous. It's been open since, I think, the early 1700s. So that would definitely secure your place in history for a long time. But not a lot of people have had luck with it. So, good rule of thumb here, back to our normal Calculus 1 land. Whenever a graph of a function can be traced without lifting your pen, is where that function is continuous. And we don't actually do a whole lot with continuity other than just kind of identifying where is this continuous, where is it not continuous. So for continuous, remember, you don't have to like go through the entire graph and say, well, okay, here at 2, my general limit is equal to my left and right hand limits, and my function value is right there on the graph, so we're continuous at 2. I'm going to move over to 2.1, etc. That would take forever. So all we really have to do is identify the places where we have discontinuities. So some discontinuities that I'm seeing here. We've got a vertical asymptote at 4. That's going to be a problem for us because our function value isn't even defined right there. Same thing right here, where we have this little hole in the graph. We do have a left and right hand limit there, but unfortunately our limit does not equal the function value because there is no function value there. It's blank. And then right over here where we have a jump or a break, that's also going to be a problem for us. So let's talk about each one of these discontinuities in what I would call a mathematically mature fashion. Because usually it's not good enough just to say, oh, that's discontinuous there because look at it. Isn't that discontinuous? It's not really enough. So let's start off with this asymptote over here. So at the asymptote, where we break continuity is that our general limit here as x goes to 4 of f of x that's equal to infinity, but f of 4 is undefined. So infinity does not equal undefined. Infinity equals infinity. So since our function value does not equal our limit, that's why we're discontinuous at x equals 4. And I know that we're talking about where the function is continuous, and we will come back to that and give a nice solid answer for that. So we would just say it's discontinuous at 4 so far. And then for this open dot that we've got up here, this has an issue because our general limit here, as x goes to 1, that does in fact exist, and it's equal to 4, because, I mean, from the right and from the left, yeah, we're going to the same place. But when we arrive at that place, our function isn't even defined there, which, again, isn't a problem for our general limit, but that is a problem in terms of continuity. If we have a hole or a break in the graph, we are not continuous there. So since f of 1 is undefined, then we have another issue here. We have our general limit as 4, and then we have the function value at that point where we're taking our limit to. That's undefined. So yeah, a little bit of a problem. Okay, let's move on over to x equals negative 4. So at x equals negative 4, this is a pretty substantial issue because our left-hand limit, so as x goes to negative 4 from the left of f of x, that is not equal to the limit as x goes to 4 from the right of f of x. So we don't even have a general limit there. If we don't have a general limit, then we definitely don't have continuity right there. That's kind of like the first part of the definition of continuity. You need a general limit. The second part is that that general limit should equal the function value. So we don't even have a general limit, so it doesn't really matter what the function value is there because, well, we don't have a general limit to compare it to.
Function value there is negative 1.
Yes, that is correct. So yeah, the function value is, so like f of negative 4 would be equal to negative 1. So we've got some issues at a few different places here. At negative 4, at 1, and at positive 4. Those are all the different places where our function is not continuous. So outside of that, based on what I can see on the graph here, I'm not seeing any problems. So that means that our function would be continuous everywhere except those values. So that means that we would be continuous from negative infinity over to negative 4. What's that? You could. I always write unions, but my math lab uses commas for some reason. So I started doing commas for that. But yeah, so union would work just fine there as well. My math lab loves commas for some reason. But and then we're also continuous from negative 4 over to positive 1. And then we're continuous from 1 to 4. Yeah. And then from 4 to infinity.